All right, today we're diving into a concept that is, well, equal parts beautiful and dangerous. It's called recursion, and it's this amazing programming technique that lets you solve huge problems with just a few lines of incredibly elegant code. But, and this is a big but, it's got a dark side, a secret that can literally bring your entire program to a screeching halt. So let's unravel this mystery, shall we? And our story actually starts with this wild legend. Picture this, a group of priests deep in India tasked with solving this ancient puzzle involving 64 golden discs. And the prophecy? It says that the moment they solve it, the world will end. Kind of dramatic, right? Well, that puzzle is called the Tower of Hanoi. And believe it or not, it's the perfect way to get our heads around the incredible power of recursion.
So let's get into it. What exactly is this puzzle? And more importantly, what's the secret hiding in its solution? Okay, so here are the rules of the game. You've got 3 rods, right? And on the first one, rod A, you have a stack of discs, all different sizes, with the biggest one on the bottom. Your goal is to move that entire stack over to rod C. Sounds simple enough, but here's the catch. There are rules. First, you can only move 1 disc at a time. Second, you can only take the top disc from a stack. And third, and this is the big one, you can never place a larger disc on top of a smaller one. See? The rules are simple, but the puzzle itself, deceptively complex.
So, back to our priests and their 64 golden discs. How long would it actually take them? Well, the math is just staggering. It would take 2 to the power of 64 minus 1 moves. That number is 18 quintillion. It's so big, it barely makes sense. I mean, even if they could move 1 disk every single second, it would take them 585 billion years to finish. That's way, way longer than the universe has even existed. So yeah, I think we can all agree the world is probably safe for a little while longer. Okay, but seriously, how would you even start to solve a problem like that? The trick, it turns out, isn't to think about moving all 64 disks at once. No, the secret is to just think about moving 1 disk, the biggest one at the bottom. And this is where we finally meet the beautiful, elegant idea of recursion. So what is recursion? At its heart, it's just this idea of self-reference. It's a function that calls itself to get the job done. Think about it with our puzzle. To solve the big problem of moving, say, 10 disks, you just tell the computer, hey, you figure out how to move 9 disks, and I'll handle moving this 1 big disk at the bottom. You keep breaking the problem down into smaller, identical versions of itself until it's so simple it's trivial. Let's walk through a super simple example of how this actually works. Imagine we have a function, let's call it f, and we start it by calling f of 2. Okay, so inside f of 2, its first job is to call itself, but with a smaller number, f of 1. And what does f1 do? You guessed it, it calls f of 0. So now we have this chain of calls, like Russian nesting dolls. But this leads to a pretty important question, right? How does it know when to stop? And that right there is why every single recursive function must have something called a base case. You can think of it as the emergency brake or a stop sign. It's a simple condition that finally tells the function, okay, that's enough, we're done breaking things down, stop calling yourself and start passing the answers back up the chain. Because without that base case, you'd have an infinite loop. The function would just call itself forever and ever and ever. So you've got this chain of functions all calling each other, waiting for an answer from the next one in line. How in the world does the computer keep track of all this? How does it not just get completely lost and confused? Well, the answer lies in a really fundamental data structure. Yeah, really. How does the computer manage to keep all of these nested calls straight without just losing its place? The magic happens with something called the call stack. And the best way to picture it is, well, like a stack of plates. Every time a function gets called, a new plate gets put on top of the stack. This plate holds all the information for that specific task. Now, the computer can only work on 1 plate at a time, the one right on top. This is a principle we call last in, first out, or LIFO. The last thing you put on is the first thing you take off. So let's see this in action. Say we call a function like factorial of 5. Boom, a plate for it goes onto the stack. But wait, it can't finish its job until it gets the answer from factorial of 4. So another plate for factorial of 4 goes on top. And this keeps going. Factorial of 3, factorial of 2, all the way down until factorial of 1. That's our base case. It knows the answer right away. So it finishes, returns its value, and its plate is popped off the top of the stack. Now factorial of 2 has what it needs, so it finishes and gets popped off. And you see how this unwinds? The results just travel back down the stack until it's completely empty again. Now, this whole process,
It's really beautiful, isn't it? It's so elegant. But it's not free. There's a hidden cost. Every single one of those plates we stacked up takes up a little bit of the computer's memory. And this is where we start to see the danger lurking inside this otherwise beautiful idea. So, what's the catch here? What's the downside? Well, all that elegance you see in the code, it can hide a very real-world cost in performance and maybe more importantly in reliability, especially when your resources are tight.
And look, the data tells a really clear story here. If you look at this chart, the blue bars, that's recursion, show way higher memory usage than the orange bars, which is the non-recursive approach. I mean, it's pretty much a constant pattern. Recursion is eating up nearly twice the resources. That right there is the cost of stacking up all those plates in memory.
And what happens when you use more memory? Well, you get more failures. It's that simple. Just look at the huge spike on the left side of this chart. When the memory was really limited, down to just 64 kilobytes, the recursive method failed a whopping 20% of the time. 1 in 5 attempts just crashed. And the other, more stable method, it failed less than 5% of the time. That is a massive gap in reliability.
So here's the absolute bottom line. Remember that stack of plates? When that stack gets too high, so high that it runs out of the space the computer set aside for it, the whole thing comes crashing down. And that crash has a very famous name you've probably heard of, a stack overflow error. It is the direct, brutal consequence of recursion's hidden memory habit.
Now, hearing all this, you might be thinking, okay, so recursion is just bad, right? But it's not that simple. It doesn't mean it's bad, it just means it's a highly specialized tool. And like any powerful tool, say a chainsaw, you really need to know when to use it, and just as importantly, when not to. This table really lays out the whole trade-off perfectly. On one side, you have recursion. Yeah, the code is often super elegant, it's easy to read, and it looks a lot like the pure mathematical idea you're trying to model. But on the other side, you have iteration, just using standard loops. It might be a little clunkier to write, but what do you get in return? Lower memory use, way more stability, and performance you can actually predict. It's a classic engineering choice.
And honestly, this quote from the research paper just nails it. It says that algorithmic elegance must be weighed against operational predictability and resource determinism. That's a fancy way of saying you always have to balance how pretty your code is with the cold, hard reality of whether it's going to be reliable and predictable, especially when you don't have memory to spare.
So that brings us to the big question, doesn't it? After seeing both sides, the incredible beauty and the very real danger, what do we make of recursion? Is it a brilliant masterpiece of computer science, or is it a critical mistake just waiting to happen in our code? Well, the truth is, it's both. Recursion is an absolute masterpiece for certain kinds of problems, things that are naturally recursive themselves, like searching through a tree of files and folders, or solving the Tower of Hanoi. But it can be a huge mistake when performance and reliability are your top priorities. And really, that's the art of programming, isn't it? Knowing when to reach for that beautifully simple, elegant tool and when to choose the one that's built for raw, predictable efficiency.